Thank you. So, bonjour. Yeah, sorry if my friend's pronunciation is crappy. It must be. I'm learning it. All right, so it's a great pleasure to come all the way from Australia, from the South Hemisphere, where it is sunny, hot weather day, and come to France. It's my great pleasure to be here. This tutorial is more about, I guess it's kind of like a summary for what I have been done in the past more than 10 years. So it's about entropies and inequality. So it's a tutorial in nature in some sense. So you may find in the first half or first 1/3 of the material, you may already know them. Please bear with me if this is too boring. I promise there is something quite interesting as we develop. So this is the first part of the tutorial. So we'll start with something very simple. Talk about what's information measure and their properties. Okay. So we all can use the terms entropy a lot of time. So what is entropy? So you may already know that entropy can be used as a measure for uncertainty or the content or the amount of information or the randomness in a random variable or in an event. So in some sense, these different concepts are all the same, are two sides of a coin. All right. So this tutorial is more about entropy and its property. In fact, it's more about not its physical meaning, but its connection to some of the mathematical areas. For example, group theory. So we'll talk about the connection here. So actually, I think a better title for the tutorial is Mathematics for Entropies. So let's start with the basic definition. So we're focusing on the discrete Shannon entropies. So let's say we have random variable, they are discrete, x and y, and their joint distribution is pxy. Right. So we'll define the entropy of the random variable x is the minus sum over px not px. We're all familiar with this definition. And we can do something similar for the joint entropy as well. Right. So basically, entropy is used to measure the uncertainty contained in a random variable. In this formula, the x naught x will be defined as 0. So you can think about if I take x to be very small and go to 0, these terms will converge to 0. So that's a reasonable assumption. Right. So besides entropy, a very common information measure is the conditional entropy. So it's defined as follows. So hx given y is given by the sum, the negative sum of px not px given y. Right. So we can write this form in a different format. So for example, if I take the py out and take the px given y here, then we can split the sum into two parts. Right. So if you look at this part, it's almost like the entropy of y given entropy of x given a particular instant of y. So you can interpret hx given y is just the average of the conditional of the entropy of x given each individual outcome y. So this all makes sense. So and you will guess that the meaning for this hx given y is the amount of uncertainty that you will have on x given you know y already. Right. So as I said, entropy is a measure for uncertainty, and it can also be interpreted as a measure for information. So how do we equate these two concepts? So you can think about this outcome, an event. I don't know what the outcomes are. If I know there's an uncertainty about this outcome, but once I know that what the result is, I know the information, then the uncertainty will be gone. So therefore, you can think the amount of uncertainty that has been removed is equivalent to the amount of information that you have gained by knowing the value of x. Right. You can do similar interpretation for conditional entropies as well. Right. So the next important concept is the mutual information. So if we're given two random variables x and y, so we can always compare the difference between the entropy hx and the conditional entropy x given y. So again, what does it mean? So hx is the uncertainty you will have when about x by itself, and hx given y is the uncertainty you have about x after you know about y. All right? So you can think about the difference between these two uncertainties is the amount of information about x that is contained in y. All right? So that's naturally will define that the difference as the information about x that is contained in y. And it turned out that this concept is symmetric. So this value is equal to hy minus hy given x. The difference will be the same. And therefore, we can think about this quantity is the amount of information that are kind of common in both x and y. So we call it mutual information. Right. And often, we'll have a special notation ixy to denote this mutual information. In some sense, this mutual information measures how each x and y knowing each other. Or you can think about they are measuring the correlation or between the two random variables x and y. And instead of defining in this the difference of two entropies, so you can also define or equivalently you can write the mutual information between x and y as this form. So they will be exactly the same thing. So if you look at this form, you can immediately see something interesting. So for example, when x and y are independent, what you will see is pxy equal to px times py. So this will be 1 all the time. So logarithm of 1 is always 0. So you see that when x and y are actually independent of each other, the mutual information is always 0. So that's a very nice and neat feature we will expect. And similarly, instead of looking at the mutual information between two random variables, we can also define the conditional version of this concept. So let's say I learn a random variable x, what the outcomes are. After knowing this additional information, how x and y will be correlated with each other. So the definition is very similar to ixy. The only difference is instead of looking at pxy, you're looking at pxy given z, and px given z and py given z here. So, and if you look at the expectation, that would be what you get.
Yeah, I'm confused about that last expression. What does that mean, or is the bracket, are the brackets where they should be?
This is the mutual information. Okay, so if you given a particular z, right, so that will induce a conditional distribution of pxy given z.
So no, I'm wondering is that gives you just conditioning on the y. Is the x variable also conditioned by that same z equals z? Z equals
Yep, z, yeah.
So I see. So it's x given capital Z equals Z semicolon y capital equals.
Yeah, this is ixy.
No,
so
x and y
ixy given z, 0 z.
not independent, but they have joint distribution, and this is conditional.
So you're only conditioning the y part. And
Conditional on z. I conditional on z here.
Okay, I was just on notation. I didn't understand.
Oh yeah, right, yeah. Okay. So let me try and explain this way. So you have three random variables here. So we want to measure how x, y are correlated given I know z. So I look at, let's say the partition, let's focus on particular z. So I know that z equal to z now. Then I can look at the conditional distribution of pxy given z. I can measure the mutual information given that particular value. And then I take the expectation of this mutual information. So that is the conditional mutual information here. All right. So again, so far we have seen a lot of these different information measures. So we've seen conditional entropy, mutual information and conditional mutual information. All right. So for all this information measure we define, it turns out that they are all non-negative. Right. That is a good feature. We measure amount of information contained in a random variable, right, or between random variables. We expect the amount of information should be non-negative. So that's a very good property. And not only that, we find that when this measure is actually become 0, they correspond to a very interesting scenario. For example, when entropy is 0, that means that the random variable x is actually deterministic. So you know with probability 1 what the outcome of x is. When conditional entropy is 0, x given y becomes 0. That means that x is actually a function of y. That means if you know y, you know for sure what the outcome of x is. Right. And when we see it before, when mutual information becomes 0, so that corresponds to the case where x and y are actually independent to each other. And when xy given z or ixy given z is 0, when the conditional mutual information becomes 0, that corresponds to the case when given that x and y become independent. Right. So these are very nice features. And actually, these inequality or equality serve a very critical role in information theory. So a lot of results are only relying on us to know this inequality. Right. And another interesting property we have is when x is actually uniform distributed over a set with m alphabet, its entropy become log m. So that's useful to know it. For example, when m is 2, it's 0 or 1. When x is uniform over 0 or 1, then it has 1 bit. So that's a very nice feature. All right. So these are what I described earlier are the Shannon entropies. To digress a bit, so besides Shannon entropy, there's a more general classes of entropy people will consider. And one of the interesting classes is this Greene entropies. So its definition is this one. So it's a class of entropies with a parameter alpha here. Alpha can be anything from 0 to infinity. Right. So there's a few special cases we are quite interested in that. So the first one is when alpha is equal to 1. So when alpha is equal to 1, you can't really define it that way, but you can think about taking an approximation limit for alpha converge to 1. So you find that the limit of this h alpha x will become the Shannon's entropy. So that is extension or generalization of, so therefore you can see that when E entropies are generalization of Shannon entropy. When alpha is equal to 0, it's called Hartley entropy. It doesn't matter what your distributions are. Its entropy is just the logarithm of the alphabet size, or more accurately, it's the support size. Yeah, exactly. Yeah. So when alpha is equal to 2, it's called collision entropy. And when alpha is equal to infinity, it looks at the maximum of px, which is and then take the logarithm of that. That's called the mean entropy.
Should it be minus that?
Yes, you're right. Absolutely, there's minus on that. So this entropy will always be non-negative. Yeah. So one of the interesting features about this class of Greene entropy is it has a monotonicity properties. So it actually monotonic decreasing with alpha. So, but the good news is when x is actually uniform, these are all equivalent. They're all the same. They will be equal to log size of the support of x. All right. So these are the definition for entropy for discrete random variable. So what about the case when x is actually not discrete but continuous? So instead of having probability mass function, we now have a density function. Right. So it's tempting to define something similar. It's called the differential entropies. It's, for example, hx is equal to the minus or integration of fx log fx. So this is a density function. So it turns out, in some sense, differential entropy and discrete entropies are very similar to each other in terms of the property, but there are also some critical differences, right? So one very important difference is differential entropy can be negative. So in this sense, it's not really right to interpret the differential entropy is the amount of uncertainty, right? Because you can't really interpret what does it mean. Similar, oops. Right. All right, let's look at some example here. So if x is uniform distributed over an interval from A to B, then it's straightforward to plug in the density function, and you can find the differential entropy is not B minus A. All right, and you can see that if this B minus A is actually less than 1, so the differential entropy will become negative. So you can see that. Right. So again, like the discrete counterpart, we can also define the joint differential entropy between two different continuous random variables. So the definition will be the same or similar. And there's some special form that I can that would be interesting to know is if you have a set of Gaussian distributed random variables, and if you plug in, and let's say M is the covariance matrix of these random variables, if you plug in into the formula, you can check that the differential entropy of this set of random variable will be equal to this one. Right. Ignoring this scalar factor, so basically this differential entropy is kind of proportional to the logarithm or the determinant of the covariance matrix M. So that is something that is quite interesting. And it turns out that by exploring this relation, we can see a connection between entropies and determinants. Right. We'll see this in the later part of the tutorial. Right. Right. So let's look at the inequalities again. Right. So in the beginning, we talked about there's a different information measure here. It turns out that these measures are also related to each other. In fact, all the information measures I described earlier, they can be represented or rewritten using only the entropies itself. Right? So that is a good thing to know. So because from now on, you can forget about mutual information, conditional mutual information, and you only need to focus on the entropies. Right. For example, what it means is if I'm interested in information inequality relating these different quantity, I can always turn the inequality into one that involving only the joint entropies. That's the good things to have. Right. So probably you have seen this Venn diagram before. But I find this is very useful to understand the basic concept. Right? So although it's very hard to draw the diagram when you have 4 or more random variables. Right. So what this diagram is showing here. So let's say we have 2 random variables, x and y. So we can draw one circle for x and one circle for y, and they intersect here. So for each of these 3 parts, we can identify a quantity to it. For example, this is the part in x, but not in y. If you think about these are containing information, this region corresponding to the information that's only appear in x, but not in y. So in fact, therefore, we call this conditional entropy of x given y. Right. Similarly, we can define this part and call this is hy given x. And when we have a part that is common in both x and y, we call this the mutual information between x and y. Right. So what I'm trying to do is if I am given an x and y random variable, and I calculate all these entropies and mutual information, I can put the numbers in this part. Right. Similarly, when we have 3 random variables, we can also do the same thing. Right. So this is the part here, which only appear in y, but not x and z. So we interpret this term as the excuse me. Yep. You can interpret this term as the conditional entropy of y, given you know about xz. Given you remove the entropy, the information about xz, this is the remaining about y. Right. So you can talk about this part as the mutual information between y and z, given that you already know x. So therefore, this is I, y, z given x. And what about ix, y? The mutual information between x and y by itself. So if you're ignoring z, the common between x and y is this part. So these two together as a sum will be the ixy. No.
What's that middle region? That's one you haven't labeled.
That's a very good question. So I didn't point out the reason for that. So it turns out it's not easy to give a physical interpretation for this term. Right. Mathematically, you can define this term as the ixy minus ixy given z. You can define it that way. But what that means is actually unclear. It turns out that sometimes for x, y, z, for some choice of x, y, z, this can be negative. So that can be negative, so you can't really associate with a physical interpretation for that one. That's the something not quite nice. But from this Venn diagram, there's something very interesting to see as well. It turns out I can use this Venn diagram to obtain some equality. For example, you can think about this term is the sum of ixy minus ixy given z. So that's this middle term. Or you can see that this term is ixz minus ixy given ixz given y. So it turns out that they are equal to each other. So this is one of the interesting things, how we can use a Venn diagram to obtain equalities. Right. So among all these information measures that we have come across so far, so there's some very useful relation between them. So one of them is called the chain rule. So that's basically a relation that breaks the joint entropy of a bunch of random variables to the sum of a collection of conditional entropy. Right. So we can also do the chain rule for mutual information. So let's say we have a group of random variables, and we look at the mutual information between this group and another y. Right. It turns out that you can break the mutual information into many sum of mutual information between x and y individually, given some other. Let me show you how this can be seen from the Venn diagram. That is an example to illustrate why the diagram can be useful to look at. Right. So look at the chain rule again. So hx, y, z, according to chain rule, can be broken into the sum of these 3 terms. If we look at this diagram, x, y, z is the collection of information in x, y, z together. That would be the whole region. Now, so to calculate this region, I can first calculate this small circle corresponding to x. So that's hx here. And then I add it to this part of the region, these 2 regions, that is hy given x. You see that this is the part containing y but not x. And then I need to add one more region here. And this region corresponding to hz given x and y. So you can see from the Venn diagram why this is true. Right. We can also look at the chain rule for the mutual information. So according to the chain rule, if I have the mutual information between x, y given z, So it can be broken down into these two terms. Right. So what is x, y mutual information between x, y, and z? So x, y as a whole will be these two circles, and this is z. And their intersection, the mutual information, will be this three part. This three part. Now, to calculate this three part, I can first look at these two parts. These two parts corresponding to the intersection between x and z. So this is ix z by itself. And then I still need to add this term. And as already seen in the figure, so this term corresponding to iyz given x. So therefore, we obtain an equality here. So this is a very useful way to recover the chain rule from the Venn diagram if you forget that, how to prove it. Right. So far, we come across with a few important inequality that corresponding to the non-negativity of the entropy, conditional entropies, mutual information, and conditional mutual information. Now, so in the following, we're going to look at some example how to use it. So I have a few more inequality to talk about first. Right. So this one is the data processing inequality. So you have three random variables x, y, z. This is a very simple version actually. So y is a function of x. So you can think about this as a processor. This is your input. So after the processing, you get a y. And then you have another processor again. You process on y and you get z. Right. And if you look at these three random variables, it turns out that it will satisfy these two inequality or equality. So in particular, hx given y will be less than x given z. Right. So and we can use a Venn diagram to see why this is the case. Right. So first of all, let's look at the criteria again. We know y is a function of x. So this is y, this is x. So given y or given x, y will be deterministic. So that means hy given x will be 0. So these two terms together will become 0. In fact, they will be 0 by itself, not the sum by 0. And the second one is z is a function of y. So given y, z will have 0 entropy. So we'll get these two terms become 0. Right. Technically, you may think about maybe the sum is 0. It could be a, this is minus a. But our requirement implies that this has to be non-negative because it's conditional entropy. This is non-negative because this is a mutual information. So therefore, it has to be 0 here. Now, let's look at the hx given y. Hx given y will corresponding to these two parts. Because it is 0, that corresponds only to this part. Right. And if we look at x given z, this is x, that will be the total of these two parts. But look at this part. This is the mutual information between x and y given z. It's always non-negative. So we see that this term will be bigger than this term. So therefore, we see the inequality here. All right, let me skip a bit. Okay, I'll give an example here how to use this inequality to obtain some interesting result. So this is a very simple scenario where we have two parties, Alex and Bob. They want to communicate over a public channel, and he wants to communicate in a secret way. So the message will not be decoded by others. So to do that, they have to share some secret key. Otherwise, they cannot do it secretly. All right. So this is the picture, what it looks like. So M is the message Alex wants to send to Bob. Both Alex and Bob will have the access of the secret key K. And Alex will encode the message X from the message M and the key. So this X will be sent across the internet, the public network. So, and the decoder Bob will take the X and take the K and regenerate M. And what you want is, if an attacker observes X, it will have no knowledge about what the M's are. Right. So that's a very simple encryption scheme. Right. But we can now try to translate this problem and using entropy to describe the problem. So first of all, we need that the system to be secure. So we need that knowing X, it gives you nothing about M. So that means X and M's are independent. So you can write it that IXM is 0, or you can write it in this form, HM given X equal to HM. The difference is actually 0. And the second one is the encoding constraint. So X is actually generated from M and K. So given M and K, X is deterministic. So therefore, we have this criteria. And the decoder, it observes X and no K's. It wants to regenerate M again. So therefore, we have given K and X, M will become deterministic. So therefore, this condition entropy will be 0. Now, from this picture and its requirement, we have this condition. So if I invoke the relation between the entropies, it turns out we can observe, or we can prove this. The entropy of K is actually greater than the entropy of M. That means the amount of key, or the secret common key shared between Alex and Bob, has to be at least bigger than the size of the message you want to transmit. Right. So I think I just skip this one. Right. These are an interesting application, but I'm not sure when I have enough time, so I'll skip this first. Right. So finally, I would like to say a remark about the Shannon entropies and the concept of Kolmogorov complexity. Right. So probably you're familiar with this concept more than entropy, maybe. So Kolmogorov complexity is a measure of how random of an object or string it is. For example, you can have a string of 1,000 bit of string, and they are all 0. And compared to a string that you randomly flip 0 and 1 for the same string, then you may probably think that the all 0 string is very not random. Its complexity is very low. Right? So Kolmogorov complexity is kind of the explanation or description of this concept. So technically, you can think about it this way. If the complexity or the Kolmogorov complexity of a string is the length of the program that is needed to generate that string. For example, you may have a Turing machine, and then you have plugged in an input, and then or a program that will print out the string. So how complicated your strings are is proportional of equivalent to how long your input or how long your program is. Right. So in that case, let's say we call Kolmogorov complexity of string of A is the length of the program that is needed to print out that string. Right. So it turns out that the Kolmogorov complexity works very similar to entropies. Right. So for example, if I have, they have an inequality similar to the mutual information. For example, they have a Kolmogorov complexity of A plus Kolmogorov complexity of B plus some adjustment term. It will be always bigger than the Kolmogorov complexity of printing A and B together. Right. So and this is very similar to the information inequality we see before, hx plus hy greater than hxy. And that is the mutual information between x and y are non-negative. Right. So it turns out it's very surprising to know that this result is true. So it was been proved that if I have an information inequality of a particular form, and I know it's true for any random variable, then it will also have a corresponding counterpart inequality for Kolmogorov complexity, just replacing h with k somehow. So that's a very interesting connection. And honestly, I'm not fully understand what's actually happening to behind why these two things will work like that. So I wish I could give you a better insight on this. All right, so that quickly finished the first introduction section. By the way, if you have any question, feel free to interrupt. All right. That is the second part. So that is the part probably is less well known. So the first part is about the basic about entropies. Right. So in the second part, I'm trying to connect entropy to different areas in mathematics and find some interesting result between them. Right. The first one is the connection to group theory. Right. So, and the first part is about generate Venn variable from groups. Right. So let's have a brief introduction of what groups are. A group G consists of two parts. One is the set G, and the second one is the group operation. So the group is a set where the operation, the binary group operation, is associative. That means if you take any element A and B from the group and an element C, if you can calculate the A circle B, and then you take the result and do the group operation with C, that would be the same as changing the order. Right? That's associativity. Right? The second important property of group is it always has an identity. So it has an element 1 such that it adds on A will always give you the same A. Right? And any elements in the group will always have an inverse. For example, for any A in G, you always find an inverse A inverse such that their operation of each other will become the identity element. It's a bit complicated, but you know groups very well. With a lot of examples, you will get in touch with, they are actually group. For example, let's say G is the set of all non-zero real number, and think about this circle is the multiplication. So that set itself become a group. So as the multiplication is associative, the identity element is the 1. And for any element, you can always take the inverse, which is 1 over A. So that is very common. Or it is the set of all integers with addition. And in that case, 0 will become the identity. By the way, I just found out that Henri Poincaré, my French will be, I'm not embarrassing myself. So I find out that a great French mathematician, he's actually introduced the group theory to the physicist and was the first one to study the group of Lorentz transform. So that's a very good, interesting thing to say here. Right. So for simplicity, you can just think about group G here is just a set, just integer with addition, for example. Right. Now, this is an interesting bit. Let's say I have a finite group G. Think about mod Q addition, for example. Right. So a set S is a subgroup of this G if S is a subset of G, of course, and S itself is also a group. Right. So let's say I'm given a set of S. Maybe it's better to give an example here. Right. For example, this is G, could be the mod 1, 2, 3. That is the group mod 4 addition. Right. So you can think about S is just 0 and 2. So it is a subset of G. And this set itself is also a group. So that is a subgroup. Right. So why do we need this subgroup? Right. Because I can use the subgroup S to generate a random variable. Right. This is the idea. Right. So let's say I have a random variable U, which is uniformly distributed over G. For example, U is uniform generated over these 4 elements. And now, for each subgroup S, this S will partition G into different cosets. So here, a coset is a subset of G, where of this particular form, it will have A circle G, where G is belong to the subgroup S. Right. So this S will partition the group into many, many different cosets. And in fact, a very interesting property is each of the cosets will have the same sign, which is the same sign as S. And therefore, the number of cosets that you will get is actually the size of G divided by size of S. Right. So that's a very famous Lagrange theorem, tells you that. Right. Let's look at an example how we can generate a one more thing. So now, I forget to mention how you generate a random variable X. Well, this is how you do it. So now you define a random variable X, which gives you the index of which coset U is actually in. So that's how you generate a random variable. Let's start with an example to illustrate the idea. All right. So I use G is the mod 4 addition, 0, 1, 2, 3. And as I said, my group G1 or S, actually in my previous slide, is the subgroup 0 and 2. Right. Now, this group G1 will partition G into two cosets. One is 0, 2. The other one is 1 and 3. Right. It is interesting to know this one. For this coset 0, 2 is equal to this element plus the group 0, 2, or is also equal to take this element plus the group is out. So they all give you the same set in the end. Similarly, for the other coset 1, 3, so it can be generated by taking 1 plus the group G1, or you can take the other element 3 plus 0, 2. They all will give you the same set 1, 3. For example, this become 1 and 3. This become 3. 3 plus 2 become 1. So it's all the same. And you can see from this example, each coset will have two elements, have same size as G1 as well. Now, let's say U is uniform distributed over G. Then the random variable X1 induced by the group G1 will take this form. Right. X1 will be the coset 0, 2 if the random variable U is either 0 or 2. It will have a different value, and the value is called 1, 3, if U is taken value of 1 and 3. It looks complicated, but it's actually just this X1 tells you which coset your U is actually contained in. Right. So in this case, we have two cosets. So X1 is actually a binary random variable. Right. So maybe after all this construction, a very key important message I want to emphasize, this X1 is actually uniform distributed. And the reason for that is because all the cosets have the same sign. So the probability that U will be in this coset will be the same as the probability U in the other coset. It is uniform distributed. And you can see right away that the entropy of this group-induced random variable is just take the log of the number of cosets, which is equal to the number of elements in group G divided by the subgroup size itself. Right. So this is a very simple, important result, which will serve as the foundation for what we want to learn later. Right. So let's look at a more thank you. Let me see. Okay, I will talk about this one first. All right. All right. So let's look at more complicated example here. All right. So we're looking at the group G is not a mod 4 addition group, but instead it is a permutation group. So you may start with a sequence. Let's say it's the sequence X. Let's say in this case it has 6 elements in the sequence. And in particular, let's say the sequence is AA, BB, CB. Now, we define a symmetric group, or the group of permutation on the set is the permutation over the index from 1 to k. So k is 6 here. Let me give an example. What is a permutation? A permutation is just shuffling the index location. Right? So, for example, I could have a permutation where I just swapping the index 1 to 6. Now, what this swapping will tell me? So I can take this permutation and add on the sequence itself. So for example, originally, it will be AABBCB. If I use this permutation and add on the sequence, where I will shuffling 1 and 6 position, in that case, the new sequence I will get after the permutation will become x6, x2, 3, 4, 5, x1. I'm just swapping the position. Right. If I know that x is this value, this sequence, then after the permutation, you will get this sequence. Right. Ignoring all the mathematics, you can see right away what permutation actually means here. Now, more precisely, this is the definition for doing the permutation. You just take the sigma 1 to sigma 6. That is the new index for the corresponding position. Right. Now, this is the one question you may ask. Right? Some of the permutation will have the property that after the permutation, the sequence will become the same as before. Right. So these permutations are the interesting permutation we're looking at now. Right. For example, here, let's say we still use x to be this sequence. We can define a collection of permutation such that after the permutation, the two sequences are still the same. And it turns out that this set of permutation forms a group itself. It's very easy to prove why this is the case. Right. And let's say you want to ask, how big is this group? Right. If you look at the permutation, look at the sequence itself, you can immediately see the size of this group is this value. How do you see it? Right. So there's a 2A, 3Bs, and 1C here. In order to make sure that after the permutation, the sequence will be unchanged. So you can only swap position between these two together. Otherwise, you will swap the sequence with another symbol, and you won't get the same sequence. So you have two factorial choices how you swap this number, these indexes. Look at the B. You have 3 positions here. You actually have 3 factorial choices of permutation. You can swapping the index, where all the B will still in the same position. And you have 1 factorial, so basically you can change the position of C. Then you can actually calculate that the size of this group is actually 2 factorial, 3 factorial, and 1 factorial. And after that, calculating the entropies of the random variable induced by subgroup is just straightforward. Just the size of all the permutation group, which is 6 factorial. You can permutate any 6 index, 6 factorial, and then minus the size of this one. That's the logarithm of this value. Right. Yep. Yep. Thank you. All right.